Alright, here we go with this one. Okay, several facts. 5,500 kilogram. You know what? It probably is best to just take a snippet of the top of this thing and just drop it right in here. Okay, so this thing is going up an incline. So it is starting at, it's starting here and it's going up an incline. Turns out the incline is 30.5. It turns out it's going 10 kilometers per hour here, and it's going 10 kilometers per hour here. So if I call this state 1 and state 2, I'll say mgh1 plus 1 half mv1 squared, okay, plus a certain amount of energy that was added to get it to mgh2 plus 1 half mv2 squared. But it turns out this value and that value are equal. So what you have is the energy is just defeating it against gravity. So the key is, how high is it going? Well, let's take a look here for a second. And it's going 10,000 meters per hour times 1 hour equals to 3,600 seconds. So we'll call that distance d. You can figure that out. That makes this distance equal to d times sine of 30.5. And that's how high it goes. So if you look at this and say, well, I'm going to make a datum in which h1 is equal to 0. Therefore, by nature, h2 can just be replaced with d sine of 30. Now, what I'm saying here is it went, and this is a big key here. When I'm finding this out and I'm saying d equals that, then this is what occurred in 1 second. So if d turns out to be like 3 meters per second, then you just say at t1 is equal to 0, time 2 is equal to 1 second. Why am I doing that? Because he wants to know the power that's required. The power in SI is usually in watts, which is equal to a joule every second, which is equal to a Newton meter every second. So if I go ahead and say this is occurring in 1 second, I can just find the top of this. How much energy does it take to shove this up every second? Well, the energy would be, what does the thing weigh? 5,500 times 9.81 times whatever d is times sine of 30.5. And this energy will be in Newton meters. But that's the energy to translate it over 1 second. And therefore, the power is equal to the energy per 1 second, or whatever E is in the number in Newton meters over 1 second. And that should be your answer. That's pretty much it. There goes that thing again. Let me pause the video and see if I want to do the other one, since it's energy as well. Yeah, I think I'm going to do both of them here because this one's energy as well. Okay, so let me snip the whole problem. Come back over here, new page, paste. Nope, nope, nope. That's weird. Try to get it again. There we go. So again, what we have here, we have the guy sitting up here with a bunch of bungee cord tied right here. He leaps off. He weighs that. It goes 60 feet. Assuming no air resistance, what's the jump velocity? The jumper's velocity just before the bungee starts to stretch. So that means it's just about to stretch at 60 feet. So I'll call this state 1, call this state 2. So it's mgh1 plus 1/2 mv1 squared. There's no added energy like the one that was adding the motor here. It's just gravity, mgh2 plus 1/2 mv2 squared. I'll set my datum at the bottom. That's what I generally do. So this is z going up. If I do that, h2 equals 0. h1 is equal to 60. He jumped starting here at a 0 velocity. So what you would have, mgh1 equals to 1/2 m2 squared, because this is 0, this is 60, this is 0, this is unknown. Cancel out your m's. Your velocity is equal to 2gh square root. That'll tell you the velocity at 2 right there. Then he says if the bungee jumper falls a maximum of 150 feet, what's the spring constant of the bungee cord? Here's what happens. Wait a minute. He falls a maximum distance of 150. So here's the guy, state 1. He jumps off down to 60, then starts stretching, goes all the way down to here. That's 150. We're going to call this state 2. Right at the end where he's just gone to his maximum, his velocity 2 equal to 0. Hey, wait a minute. Velocity 1 is equal to 0 as well. But what happens? Well, from this point to that, you're getting a stretch. And the energy from the stretch, 1/2 k times the stretch squared. So what we have to do to make it complete, mgh1 plus 1/2 mv1 squared plus 1/2 k delta squared 1 equal to, guess what I can do? Let's do a copy. I'll paste it. But what I'll do, state 2, state 2, state 2. Let's identify. First of all, like me, I like to pick the bottom as the datum. So this means H2 is equal to 0, H1 is equal to 150. That goes away. That goes to 150. This says the initial velocity is 0. And guess what? The bungee cord's not stretched when the guy's sitting on the platform. Guess what? It's completely stretched, and that's 0. So what do you get? All the potential energy gets transferred into the spring energy. mg h1 is equal to 1/2 k delta 2 squared. You can figure out the stretch because it's just 150 minus 60. You move everything around and you can find k. 2 mg h1. That's it. So let's see. Oh, that's right. I had it. No. So he tells you the spring stiffness and the velocity. I'll go ahead. I don't think this was even 10 minutes. Oh, wrong. 11 minutes.